Hi everybody, this is Mrs. Ellsworth. So far we've talked about these things in motion mapping too and graphing, and so we've been talking about how things move and what their motion would look like. Now we're going to talk about the equations that we use to describe the motion too. So we are moving forward into using equations. Okay, here's our first example of an equation. And you'll notice it says average speed. Average speed is shown with a cursive V, hang on, with a cursive V, and it is the average, okay? And so write this down on your notes right there in the middle of the third page, okay? Anyway, where it says formulas, okay, here's our formula. We've got the average speed, and it is abbreviated with V average. This is kind of like a subscript here. Okay, distance traveled. Okay, in ninth grade, we might have just done a D. Okay, and you can do a change in X also, or else you can do a change in D. Okay, that triangle there is delta, and it stands for change in. Anyways, I'm just going to put a change in D. You could put a D in there too, only a D if that makes you happier. And the time taken. So that is a whole time period too. And I'm just going to put this here just so that I can denote that to you, to let you know that, wherever it starts taking off. So like, let's say you're taking a trip and you're going to pass something. And at the beginning of that time that you're passing to the end of the time that you're passing, that'd be during that time period. It wouldn't be during your whole trip. Anyway, I'll go and also manipulate these formulas too. So if I was going to go and solve for time, you can put t or change in t, okay, and that's going to equal what? Well, I would just go and say that it's taking the distance or the displacement, okay, and dividing it by the average velocity. Okay, we can also manipulate one more time, and you should be writing down all three of these, and later on transfer them to your formula sheet that we use, because those will help you tremendously in organizing those so that they help you all throughout the year. Okay, because this is not the only time we'll talk about average speed or acceleration later on too. Okay, so to solve for D, okay, I'm going to shorten mine up here because I'm running out of room. Anyways, we're going to multiply these two. So it's going to take the velocity times time. And I shortened them up, and that's okay. You don't have to always have that, but just recognize this during a certain time period. So there's 1, 2, 3 variations of this main formula right here. Okay, let's use this information. If you drive a distance of 40 miles, or 640 kilometers in 8 hours, what is the average speed? Now you could probably see that we would be using the V average equals distance divided by time. Okay, and we don't really need to figure out what the span is for the distance here of this, because it gives us how many. It's starting from 0, so you don't really need that change in. Okay, anyway, so we would have, if you would use these units, you could probably see easily that that'd be 50 miles per hour. Okay, that's fine if you're only giving that. But usually when you're giving some metric stuff, please try and use this one. So 640 kilometers, okay, and it's during an 8-hour period. Please show your units in these so that you can see exactly what your units of your answer is going to be. So when you go and do these calculations, that's pretty nifty. I can already see that I've got kilometers per hour, and that is nifty to know. So 640 divided by 8 is 80. Hello. 80 kilometers per hour, and that's a good answer. That is our average speed. Okay, moving on to the next problem on the sheet. Okay, problem number 2, you're traveling at 35 miles per hour, or about 50 feet per second. So we've got a couple of nice little information here. Now these right here are miles per hour and feet per second, so these are both some average speeds. Okay, they're both average speeds. We don't know which one we need yet. And your reaction time is 0.2 seconds. Okay, we always used to teach reaction time, but we've kind of cut it out because it's not a standard, of course. And anyway, so we got seconds here though. So that means that this one is really nice because you've got the seconds there. So I'm going to just ignore this one because when you look at this, I know that I'm going to have these canceling out. There is no metric in here, so I'm going to use the feet per second so I don't have to go in and do any converting. It's done for me right here. Okay, calculate the distance that you travel. So distance equals the average velocity times the time period. And so then we can go ahead and do that really quick. And we've got 50 feet per second, okay, times, and notice how I'm using those units, 0.2 seconds, okay, and so that's going to be 10. What is my unit going to be? Well, this is just lovely because seconds will cancel out, okay, and you'll just have feet left. So it takes 10 feet to stop, and that doesn't surprise me when you're talking about going something so slow, when you're doing a quick stop. So there we go. That's the distance it took to stop. Okay, moving on to number 3. Okay, in an automobile collision, it was determined that a car traveled 150 feet before brakes were applied. Okay, so if you've got a reaction time here, this could take quite a while. It depends how fast the car is going. Okay, so let's think about this for a second. If the car had been traveling at a speed limit of 40 miles per hour, okay, or 60 feet per second, what is the driver's reaction time it took for it to brake? So we want to know the time. Okay, so here's the time. Okay, and notice that we've got feet up here, so we're not going to use this 40 miles per hour. We're going to use this little bit of information here. Okay, so the time that it takes for this whole thing happens with distance divided by average speed. Okay, and we're going to get that to be 150 feet divided by 60 feet per second. Okay, and so if you go and do that, 150 divided by 60, you get 2.5 seconds. Okay, let's just take a moment here and remind ourselves about units here before we go on more with the problem. We've got feet up in the top, okay, and then the bottom is feet per second. So if you go and flip this and multiply like you're supposed to do with fractions in math, second over feet. And maybe you could see what canceled out here easily. Okay, anyway, so the feet cancel out. I already flipped this one and multiplied it. So you got just seconds. So that's really nice because if you set these up correctly, your units just pop out. Okay, and that's great. So then you don't get a portion of your problem wrong. So if you just go and take your time to go and look at this, it really can help you be successful on some of these problems. Okay, so 2.5 seconds. Boy, that's a long time. Witnesses said that the driver appeared to be under the influence of alcohol. Does your reaction time of your data support the witness testimony? Well, let me just go and say that over the years while we were always teaching about the reaction time of students, it was always less than a second. Even our slower students, even your old teacher here. I would sometimes have a slower reaction than students, but it's always just a fraction of a second. So this person took a long time to react, okay, because they probably saw some of the markings on the ground for that. So that probably would support it because it took so long for them to react. Okay, so yes, long reaction time. Very long reaction time. Sorry, I always abbreviate reaction. Okay, so moving on. Okay, so in your notes there in the bottom of the page, you can go and remind yourself about what does speed mean. Okay, so speed, if you remember right, is the amount. Oh, geez. Sorry. Anyway, speed means the amount of time, the distance that it traveled during a certain amount of time. We've got these already defined on the front page. Okay, and velocity is the speed also. Okay, the distance divided by the time, the amount of distance that occurred during a certain time period. Okay, and direction. Okay, and then we also talked about, in the very beginning too, we talked about acceleration. Okay, and that means how fast something's velocity changes. So that's still got some direction in there too. So the which one of these ones are vectors? Well, a vector is a quantity of anything. So it could be speed or velocity, but it also includes, okay, magnitude is usually a value like 55 meters per second or miles per hour, okay, and direction. Okay, direction. So this one had direction, so this one is a vector. Okay, this one will be a vector because it's talking about the velocity changing. Well, it's going in a certain direction. Okay, and so that means that these ones right here are vectors. And what we can't see back here is speed, and speed itself is scalar because it does not include direction. Okay, so there's a little bit of extra information there for at the bottom of your page. But I'm going to keep moving on. So pause if you need to take more time. Okay, and just a reminder too that that speed, the change in velocity, is acceleration, right? Okay, that can happen when you speed up or when you decelerate and slow down, but it also can be when you're going 55 miles an hour around a curve and that you are not changing your speed, but you're changing your direction. So for these three cases right here would all be changing in velocity or acceleration. Okay, and go ahead and take a moment and fill out these ideas here. And I am going to stop this video because class is about to start, and I will have those answers for us, and then we will also go over the acceleration formula in the last of your notes.